All right, here's a brief lesson on section 1.3 from the text that's got to do with continuity. When is a function continuous? So part of what I want to do is slides I've got on lecture slides is what they're called in sampling. This is what the lecture slide looks like. And this slideshow that I have set up for you, you can get on through sampling. But the idea is, in this one in particular, lecture slides 1.3. All right. The first thing I want to talk about is section 1.3, continuity. And the one thing I want to talk about in this lesson right here is just the very first objective that's listed here is determine whether a function is continuous at a number. Another one that we'll spend a little more time with is got to do with when is a function continuous and the properties. That's a little bit downstream. But I will be getting to those soon. But let's just talk first about when is it continuous at a number. So first, is a function continuous at a number? Look at these three examples and take a stab at it in yourself. You're thinking, are any of these continuous? Is more than one continuous? Stop and think about the situations, and shortly we're going to go through the definitions in such a way that you will know. I mean, it'll be no doubt in your head. We've got something here, a little different thing here, and then we've got this. Are any of these considered continuous? All right, so let's go down and take a look at something else here. Is a function continuous? Here's another two examples of functions. And let's go back to this and say it does turn out that one of these is continuous and the other two are not. We'll talk about why in just a second. Okay, these two are not continuous. Let's get to the definitions here. Definition of a continuous, to have continuity at a number, for a function to have continuity at a number. Function f is continuous at c if the following three conditions are met. First, f of c, the value of x at c is defined. So it is included in the function. Then, the limit as x approaches c, usually that means we got to check it from the right and from the left to see, is it going to the same place? And if it exists, then that's one of the criteria to be continuous. And then the last one is that first definition, that f of c is defined, well, the limit also has to equal that f of c. Okay, and at the bottom here, it does say, whenever one of these three conditions is not satisfied, the function is discontinuous at that situation. Okay, let's go back up here. Tell you what, let me go up to show you. Let's put the rules side by side beside a graph of those three graphs that we were looking at here. Okay, all right, and now I think you're in a position to be able to see that by looking at this. Is that right? Can you see those three graphs and see the rules here? Let me hold on one second. Yeah, good. Okay, so look at the situations here. Look at them and verify circumstances here. And let's define these two are not continuous. Let's go to seeing why not. Let's look at this one right here. The first definition criteria that has to be met. F of c is equal to 0 in this case. The x value is equal to 0. That's what our point of concern is. F of c is defined, is the first step. There is no f of c. F of 0 doesn't happen. It's not defined. There's a hole there. So this might be a function because it passes the vertical line test, but there's a hole in it, so it's not continuous. You got to lift your pencil in the process of doing it. Look at this, okay, and then we look at this one down here. Is f of 0 defined? Yes, in this case, f of 0 is defined. We've got a dot here. So we've got f of 0 defined in this piecewise defined function. We've got a definition. When x is 0, the answer is 0. Boom. Now the second one. The limit as x goes to 0 exists. As you come in from the right, you're going to a specific spot, and as you come in from the left, you're going to the same spot. That means the limit does exist. So this second criteria is also met here. Notice the third one. The limit has to equal f of c. That criteria is not being met. And as a result, this function is then discontinuous at x equals 0. You have to lift your pencil again. And that's the circumstance. Then if you come back to this, you can see, look at the one that is, look at f of c. F of c is defined. F of 0 is defined. It's filled in point there. The limit exists, coming from the right, coming from the left, going to the same place. And they're equal to it. That limit is equal to the value of f of c, excuse me. So that is a continuous function. Okay, so let's continue on down just for a second. Look at these two. There's a couple other terms I want you to get down before we leave this. I think you can see that these two are not continuous at the number, okay? This is not even defined at x equals 0. So it's not, but this one is defined, but you have to lift your pencil in order to complete the graph, okay? So continuity at a number, the 3 rules. Let's take a look at this example here then. So if going through the 3 rules, I'll keep the 3 rules up here on the right here, but determine whether the parabola, x squared, the quadratic function, is continuous at 1. Going through the rules, if you were asked to go through the specific rules, the 3 rules you got to fulfill, you would check first. Plug in 1 to the function. Is it in the domain? Yes. Is it a legal number? Yes. F of 1 equals 3. That is in the domain. There's a function. Second, does the limit exist? The limit as x goes to 1. You come in from the right, you come in from the left, you're going to the same exact place. Therefore, it's cool. The limit exists. And the third thing is that that limit is equal to f of 1. So it does exist. The 3 conditions are met. It is a continuous function. Now, there's circumstances where, other than that fact, you know, when one of the 3 facts isn't true. So looking at this example right here, determine whether, first of all, you guys, look at this. Can you factor the top? Can you factor the numerator? Can you factor the denominator? Get a handle on remembering that you can factor the denominator. That's a difference of 2 squares. Can you factor the numerator? No, it's a sum of 2 squares. Remember, that is not a factorable situation. And we'll talk more about that on another class. You can ask about it. The top is not factorable, the bottom is. But the question is, determine whether g of x is continuous at 3. Well, you can see this factors into x plus 3 and x minus 3, and plugging in 3 causes x minus 3 to be equal to 0. And looking at the graph, and I do want to remind you, use your calculators, use Desmos. Look at a graph, use it as a tool to answer the question. Is it continuous at 3? You see this, you can say no. If I ask you for a reason, then you need to know the rules to understand why, and tell me why. But it is not. It's not defined at x equals 3, so it's discontinuous at 3. Here's one more situation that I think is worthy of note. Here's 2 terms I want you to know, okay? 2 terms that I want you to know. It's got to do with this type of an arrangement right here, the difference between these 2 functions. And look, one of these terms is called, it's got to do, they both have to do with discontinuities, but one is removable and the other is called a jump. A removable discontinuity versus a jump discontinuity. A removable discontinuity is such that the discontinuity is removed by defining or redefining the value of concern, okay, the whole. Whereas a jump discontinuity is if the limit exists when they come together, but the limit from the right and the limit from the left are not the same value. So for instance, this situation right here, this has a removable discontinuity because of the fact that if I define this function at x equals 3 and called it the value that it needs to be to fill that hole, it's no longer a discontinuity, okay? At x equals 3, if I said f of x equals 6 at x equals 3, then it's continuous. So that means it's removable. This function over here is such that no matter what, if the dot wasn't there, that was a hole, that would definitely be a discontinuity. If I filled either this or this, the limits are not coming to the same place. So it's still discontinuous, even if you fill one of the holes. This is called a jump discontinuity. This is called a removable discontinuity. And if you go back to those original 3 examples that we worked with from the beginning, that you can see that this is continuous. This is a discontinuity, because if we define the function to be this value at x equals 0, then it would be continuous. And the same thing here. If you rename this so this function wasn't 0 but was this value, then it would remove the discontinuity also. Notice on these two, both of these, it will not be continuous if you fill one of the holes. Therefore, both of these are jump discontinuities. Okay? So that's the information I want you to get from this situation, from this continuous, section 1.3. I'll come back later and talk about more about the continuity on an interval, and we'll go from there, okay? Be well.